Okay, here is video 2 of chapter 1, and we start talking about units of measurement. So here we have different types of measurements that we will be working with. Something like mass or length. It's kind of like if I said the table was 12, you would need to know what I mean. So 12 grams would mean I was talking mass. 12 meters would be saying I was talking about the length. So here are set units, the SI units, which stands for System International, for each of these different quantities. The bottom couple we will not work with. The top 4 is what we'll work with here in this chapter. But you can see the kilogram, the meter, the second, and Kelvin. And we'll work through each of those as we go. So volume is the amount of three-dimensional space an object takes up. Volume is not in the listed table up here because it's derived from length. So for example, you can get the volume of a solid object by taking length times width times height. If you do that, you would have a meter, and a meter, which would make you meters cubed as one possible unit. Or if each of these were in centimeters, it could be centimeters cubed. So any length cubed will be a unit of volume. You also can use a liter or a milliliter. There are other prefixes we'll run into as well. But we want to know liter is always talking about volume. Same with length cubed. Another helpful thing to know is that 1 milliliter is the same thing as 1 centimeter cubed. So if you had an object that was tiny, 1 centimeter by 1 centimeter by 1 centimeter, that would be the same size as a milliliter. It'd be a tiny, cute little box. Density is another one that's derived from multiple units because it's mass per unit volume, which means it's got to be some kind of mass unit over some kind of volume unit. For example, gram per milliliter, gram per centimeter cubed, kilogram per kilometer cubed. So as soon as we see that type of unit, we know that that's going to be density that it's referring to. Here's our equation for density, and we'll be back to that later in the chapter. Temperature can be in Celsius, Fahrenheit, or Kelvin. We do not work with Fahrenheit very much in this course, or science in general. We work with Celsius and Kelvin. These two go very well together. You'll notice here it tells you how to convert between different units. And Kelvin is really especially helpful because it will never be negative. That's because 0 Kelvin is known as absolute zero, where molecules are understood to stop, meaning you can't get any colder. So Kelvin will never be negative. And Kelvin and Celsius go hand in hand. They just differ by 273. So when we're taking measurements, we have to care about units. We also have to care about this thing called significant figures. So here, what we'll see is we have to understand accuracy and precision a little bit. Accuracy is how closely individual measurements agree with the correct or true value. So really, how good is your equipment? How close is your piece of equipment getting you to the actual value? Precision is how closely individual measurements agree with one another. So you can be precise, but not accurate. If you get repeated measurements that are really close together, that's precision. You may be accurate or you may not. So if you have a scale that's miscalibrated, it may give you very good precision, but really poor accuracy. We end up looking at accuracy more here. That's why we use what's called significant figures. Oops. What significant figures do is that they ensure that measured values only have one estimated digit. Okay, so for example, if you were using this ruler to get the length of this piece of wood, you know without a doubt that it's 4 centimeters. We all agree with that. So this 4 is not estimated. But the next value is estimated because there's not any smaller tick marks. So 4.5 centimeters would be how we record this length. Now, if you thought 4.4 or 4.6, that's fine, because this one value right here is the uncertain or estimated digit. We never want to put numbers after our last significant figure, or our estimated digit, because we don't want to estimate more than that. That would be really making up numbers. If you look at the second ruler, it gives a little bit more accurate reading because it actually has tenths. So we now know that this is 4.5. The 0.5 is no longer estimated, but there's no additional smaller tally marks in there, so 4.52. I'm now guessing at the 2. It is okay to guess on one number. We just don't want to go beyond that. So now we get to go one extra digit. And then just a third example here. We're back to just the whole numbers. 3. 3 is not the estimated value, but the 0.0 is. And that 0 is important because if I left off the 0, they would now think that I don't even know the 3. But I do know the 3. I just have to put one more digit to show that that's the uncertain value. Here are the rules for significant figures. Anything that's not a 0 is significant. So 22.2, all 3 are significant. There's 3 sig figs, and that very last 2 is the estimated value. Zeros are the complicated numbers. If there's a 0 between 2 significant figures, then it's automatically significant. I call these captive zeros. So 20.3, the 2 and the 3 are significant, and the 0 is as well. This 3 right here, the last significant figure, is always the estimated digit. Zeros at the beginning of a number are never significant. The leading zeros, they can also be called placeholders. These zeros at the beginning of a number are never significant. You totally skip them. They're important to be here, but not significant. So here, meaning this has 2 sig figs, and the very 2 at the end is the estimated value, estimated digit. Zeros at the end of a number are a little bit trickier. Okay, so here if we see 500, the 5 is significant. These trailing zeros right here at the end are not significant. If you see a value like this where there is a decimal point, then all of the trailing zeros are significant. So it depends on whether there's a decimal point. This guy, no decimal point, they're not significant, so that is only 1 sig fig. 500.0 has 4 sig figs. The difference is in this first one, the 5 is estimated. We don't even know that number. But in the second value, the 500 is definite, and this very last 0 is the only estimated number there. So very different accuracy. And then you have exact numbers, which really don't have to deal with significant figures because there's no estimation. If I count 5 textbooks, that means there's exactly 5 books. There's infinite number of sig figs. It's not a measured value. Conversions can also be exact or not. I didn't put an example here. I'll show you one as we go, but some conversions are exact. Most of the ones we deal with, we will assume are exact. Like 1 foot is exactly 12 inches. There's no estimation. 1 minute is exactly 60 seconds. Those have no estimation in them, therefore are infinite sig figs. Here's a few practice problems you can run through and see the rules of sig figs. Once we are to continue to use correct number of significant figures. So here, rules for significant figures and calculations. We first have to know how to round really quickly. What you're going to do is underline all of the significant digits. So you underline the significant figures, and then you look at the first non-significant digit. And if it's less than 5, you round up, and if it's less than 5, you round down. Let me show you. Here, if your calculator gave you 8.4234, but you can only keep 2 sig figs, okay, you and the first significant figures, which is the 8 and the 4. So the 8 and the 4 are significant. I really should have only underlined those. And then the 2, you look at the 2 to tell you, does the 4 need to stay or does it need to round up? Well, because it's less than 5, the 2 is less than 5, it's going to leave the 4. So 8.4 would be 2 significant figures. If you needed this to go to 3 sig figs, you'd keep the 8, the 4, and the 2. You look at the next 3, and the 3 tells the 2 to also stay. So 8.42. Okay, 14.780. Whoopsie. Okay, if you want to keep that to 2 sig figs, the 1 and the 4 are the only 2 places you can keep. The 7 tells the 4 to round up to a 5. So 15 would be 2 significant figures. 3 sig figs, you would be able to keep the 1, the 4, and the 7. You look one beyond, which is an 8. The 8 tells the 7 to round up to 14.8. Okay, so when you'll use that is when you're adding or subtracting, multiplying, or dividing. So there's different rules for these. For addition and subtraction, you're going to look at the least number of decimal places. Very important, decimal places. So if you're adding 5.0 and 1.22, you look at decimal places. This guy has 1 decimal place. This one has 2. And you're always limited to the least number. So your answer here can only have 1 decimal place. So I rounded it to 6.2. Here, if you have 12 meters plus 2.2 meters, you have 0 decimal places, 1 decimal place, so you can only have 0, meaning you have to round to 14 and ignore what comes after that. Multiplication and division, you go to least number of sig figs. So for example, if you are multiplying to get volume here, you take 2.0 times 0.001 times 3.22. You have to go through and look at the sig figs. There's 2 here. You can go back and review your rules. There's only 1 sig fig here, and there's 3 sig figs here. So if I have 2, 1, and 3, I am limited to only 1 sig fig, which means my answer has to be rounded down to 1 significant figure. So if my answer in the calculator comes out to be 0.00644, the zeros are not significant because they're placeholders, they're leading. I can keep the 6, and the 4 tells the 6 to stay a 6. And here's one mixed example. So 3, if I've got subtraction on the top and then followed by division, you follow each rule as you go. So if you subtract on the top, if you subtract, you're looking at decimal places. So 3 decimal places and 3 decimal places. So I will go ahead and round that top value to 3 decimal places, which means I really actually went too far here. So there's a mistake here. 1.039 minus 1.020, it actually should only have 3 decimals on the top. So it should be 0.019, 0.019, and then divide by 1.0390. Well, now that you're dividing, you look at number of significant figures. So the bottom has 4 sig figs. Not sure where I got my extra O. 4 sig figs. I'll update this on the filled in notes. And the top only should have out to the 9, which would only be 2 significant figures, the 1 and the 9. So we're going to have 2 sig figs on the top, 4 on the bottom. We divide and we can only keep 2 sig figs. So the actual answer here should be 0.018. That 3 should not be included because we actually can only take this to 2 significant figures.